So the final control structure we need to talk about is an if-else block, which we'll be using to check if a certain condition is true or not. Just a basic example of what we're going to do. Let's drop down a GeoNode, dive in there, and use the add sub to add a single point. Next, let's drop down a point wrangle, and on here just initialize an attribute, call it out. It should be a string, and it should be empty for now. Let's head over to the Geo spreadsheet and check. Yeah, empty string called out. Alright, let's append another point wrangle, and in here let's first define 3 variables. Let's call them A, B, and C. Let's set A to 5, B to 6, and C to 7. Okay, let's assume for some reason we want to check if B is bigger than A, and only then do something. The way we're going to do it is with an if statement. So we're just going to drop down if, then our parentheses, and then our curly bracket, similar to our for loop structure. And in the parentheses, we will write an expression that Houdini will then evaluate. And if this expression evaluates to true, so if this expression is met, then Houdini will execute the code block that's within the curly brackets here. So let's write down an expression, and we want to check if B is bigger than A. And if it is so, let's set our string out to true, like so. Click outside here, and we can see our string is now set to true, because B in our case is bigger than A. 6 is bigger than 5. Okay, let's set B to 4 in our case. We can see now this expression here evaluates to false, so this code block here is not executed. However, it bugs me that this out attribute is just empty. So what we can do in this case is we can use an else statement, which just goes below this curly bracket here. Just write down else, and then again curly brackets. So we now extended our if block so that we check this expression here, and if it's true, we will execute this code block here, and if it's not true, we will instead execute this code block here. So let's write in here, our attribute out should in this case be set to false, like so. We can now see our output string is set to false. So this is the very basic structure of an if-else block. And as you've seen, you can use the if statement without the else statement, but you cannot use the else statement without an if statement. However, what you can do is you can combine the else statement with another if statement. So first we want to check if B is bigger than A, which in this case is not true, so we'll go to this else here. And in this case, we can now check again if, for example, B is bigger than C, which should evaluate to false. And we can see now this code block also does not get executed. And of course after this we could drop down another else, and so on and so on. So you can combine these else blocks with another if to build more complicated decision trees, decision structures. But for now let's get rid of that. And let's again look at this expression here. So what I can do is I can check if something is bigger than something else, if it's smaller than something else, if it is exactly equal, which we're going to do with those 2 equal signs. So now these numbers have to be exactly the same, which they are not currently. So let's just set them both to the same number. We can see now this evaluates as true again. And we can also combine expressions. So let's set our variables to 4, 5, and 7 in this case again. And let's first check if B is smaller than A, which is false. But let's also check if maybe C is bigger than B. And the way we can do this is with logical statements. And the first logical statement is the OR statement, which is these 2 vertical dashes. So we'll check if either B is smaller than A or if C is bigger than B. We can see now this evaluates to true, because one of these conditions is met. It doesn't matter which one is met. In this case, it's the second expression here, but this one is true, so the whole block here gets executed. This is an OR statement here. So this lets Houdini check if any of those statements is met. And we could add a few more, so we can also check if maybe C is exactly equal to B, and so on and so on. And this logical combination of expressions here is just evaluated left to right. So this one is evaluated first, then this one, and then this one. And if any of those is met, the whole block here will be executed. So that's the logical OR. However, there's another operator. So in our case, let's first check if B is bigger than A. But we also want to check if C is bigger than B, and only if both conditions are met, we want to execute this code block here. The way we do that is with a logical AND, which is those 2 ampersands. So we want to also check if C is bigger then B. And we can see now the first expression is true and also the second expression is true. So this one here gets executed. Let's just try to negate this. So now we check if B is bigger than A, which is true. And we also want to check if C is smaller than B, which is not true. And in order for this whole expression to become true, both sides here have to be true, which is not the case anymore. So let's check, and we can see now this evaluates to false. So this is the logical AND operator, which means that all of the expressions that I combine with the AND operator have to be true in order for the whole expression to become true. So let's get rid of that here. And the last thing I want to show you is kind of a shorthand. So if you have an if statement whose code block is only one line, you can omit those curly brackets here. And same goes for the else statement, and it'll still evaluate, and evaluate correctly. Let's just check. Yeah, still works. So this is kind of a shorthand. If you have only a short expression and only want to execute one line of code after you checked your statement, you can just do that. Okay, back into our previous setup. Let's just delete this one. You know, this was the clumsier one. So let's just go with the for each version here. What we want to do now is check not only if the points we're looking up, the near points we're looking up, is within a certain distance, but also if it has a minimum distance to the point from which we're looking. So let's create a new slider, call it mindist for minimum distance. Should be a float value. Let's call it min_dist. Create the slider, and let's set a minimum distance of 0.4 for now, and we can change that later. So the maximum distance is already checked when we're looking at those points. And in order to check if the points have a certain minimum distance, I'll just do this in this for each loop where we draw the polyline here. But before we draw the polyline, let's first get the distance from our currently active point to the point that we want to draw the polyline to. So let's create a float. Call it dist for distance, and it should be equal to the distance between my currently active point position and my point position from the point npt. So let's get that first. Create a vector, let's call it npos, and it should be equal to the position of my point that we're currently iterating through. Like this. So we can now calculate the distance between our currently active point position and the npos, that is the position of the target point. Let's check. Okay, no errors so far. And now what I want to do before I draw this line here, I want to check if the distance that we just calculated is bigger than our minimum distance. Like so. And only if this is true, we want to execute this add prim here. So in this case, we could use the shorthand, and let's increase our minimum distance here. And we can see now the closest connections don't get drawn anymore as we increase the minimum distance here. All right, so far, let's extend on this a bit. And just for demonstration purposes, let's create a box and append the points from volume. Highlight this here and maybe scale up the box a bit to say 10 by 10 by 10. And in the points from volume, let's increase the point separation to dial back on the point density a bit, like so. And let's just copy over this point triangle where we connect the points, and let's highlight it. And also, let's dial down the maximum distance and the minimum distance to 0. And we can see we now get this regular structure of these interconnected points. Let's add another control for that. That is the maximum number of points we want to look up. So again, let's in this case create an integer, call it max pt, and it should be equal to an integer slider. Let's call it max_pt_num. Like so, create the slider. In our case, let's set it to maybe 5. And in our near points function, when I highlight it, hit F1, I can see I have the option of calling this function here with a maximum number of points it should look up as a last argument. So let's do that and just add our max pt number back here. And we can see now we can dial in how many points we find, which is already yielding some kind of interesting structure here, especially like this here. And maybe let's randomly delete some points here in the volume. Let's do that also with the point wrangle. And for each point, let's just generate a random number. Let's use our trusty old rand function, just feed it the point number here, plus some sort of seed. So let's just go with the 1, 2, 3 here. And we want to check if our random number, which is randomly between 0 and 1. So if it is smaller, say 0.5, then let's just remove the point we're currently working on. So again, let's hit F1 on remove point, and this takes two arguments, our current geostream, which is the 0, and the point number it should remove. So 0, comma, at btnum, like so. We can see now we randomly deleted about half of the points here, which looks a bit more interesting. However, what bugs me are those diagonal connections here. So let's update our connect points here so that it will only connect points in a rectangular fashion. And how do you do that? Let's look at this two-dimensional case. And what we want to allow are connections like those here, like the blue one. And what we want to restrict, not allow, is connections like the orange one here. And also we want to allow connections like these here. So what's the difference between those blue connections here and the orange one? Well, for the blue connections, only one component of the position, in this case the y component, and in this case the x component changes. However, for this connection here, the point position changes both in x and y. So the point's position vectors, x and y components, both change. So what we have to do is we have to check if the difference from our target point and our currently active point only changes in one component, be it x, y, or z. And as soon as this difference changes in more than one component, we don't allow connections. So the way I'll do this is I will first delete those two statements here, and after I looked up my target vector position, I will build three float variables. Let's call it xdist, ydist, and zdist. And what we want here is we want to have the difference between our currently active point's x position and our target point's x position. However, we do not care about the sign, so we do not care about if this difference is negative or positive. We just want to have its absolute value, so let's take that, just using the abs function, like so. Let's copy this line, paste it 2 times, and change it. So we'll calculate the y distance and z distance by subtracting the y and z components respectively. And now we're gonna write a nightmare of an if statement. Let's drop it down like this. So we want to draw this line only if one of those components is bigger than 0 or bigger than a very small threshold. So let's check first if our xdist is smaller than our threshold, and let's take a very small number, say 0.001 here. And if our x distance is almost 0 and our y distance is almost 0, then let's draw this primitive. Let's just check if that works. Okay, we're now drawing primitives along one axis here, but also we want to allow this primitive to be drawn if only the y distance and the z distance are close to 0. So let's drop down a logical OR. So this code will be evaluated either if this condition here is met or if the condition I'm just going to drop down now is met. So y distance is close to 0 and z distance is close to 0. Again, this yielded another axis here, and let's add the third axis again with our OR statement, and finally want to check if x and z are close to 0. So xdist smaller than 0.01 and zdist smaller than 0.01. And now we've drawn all those connections in all 3 axes, omitting those diagonal connections, also when we're cranking up the connection point number here. Okay, we now have this kind of Borg cube structure here, and that's one half of the setup that we need to render this tutorial's intro video. And the other part is a subdivision algorithm that we're going to build in the next tutorial.